Welcome to EDU World Space.
We're given the following situation with two spheres in space where no other forces can act on them except their own gravitation. So we have m1 of 50 kilograms and then 40 meters away, m2 of 100 kilograms. We're also given the radiuses of the sphere, but that's not going to matter because they're never directly touching each other. We can always just treat them each as point particles. So I'll just treat them like that here. So first we're asked to explain in part A why linear momentum is conserved. So you can answer this a lot of reasons. I think a fairly intuitive one is just that there are no external forces. So the only forces acting are m1 on m2 and m2 on m1. So that means that the total momentum of the system must be conserved, can't change. So P initial has to equal P final. So part B then says when their centers are 20 meters apart, we want to find the speed of each sphere and then the magnitude of the relative velocity of each sphere. So that'll be now when they've moved from 40 to them both being a little bit closer to each other and now only 20 meters apart. So we'll do this with conservation of energy. So we'll say that the initial energy must equal the final energy of this system. So we have an initial kinetic energy plus an initial potential energy, and then we have a final kinetic energy plus a final potential energy. So initially the spheres are at rest, so this initial kinetic energy is just zero. So we only have our initial kinetic energy, or sorry, our initial potential energy, so negative g masses of the two spheres, and then divided by their initial distance of 40 meters. And then we have that equaling the final kinetic energy, and then the final potential energy, so negative g m1, m2, and then the final distance of 20 meters. So we can get then that the total kinetic energy in the end must be negative g m1, m2 over 40, and then plus g m1, m2 over 20. And so we can evaluate that and we get 8.34 times 10 to the minus 9, so nanojoules. So that'll then help us figure out what the velocities of them are. So we need to actually rely on this fact from part A that there's no external forces and so that the initial momentum must equal the final momentum. So because the initial momentum is zero, that means the final momentum must always be zero. And so that means that these two masses have to have equal and opposite momentums at all time. So we can say, assuming m1 is traveling to the right in the positive direction, then we'll have m1 v1 and then plus m2 v2. So the momentum of each of them has to be zero at any point. And so we can solve for v2 then and say v2 needs to be negative m1 over m2 times v1. And so m1's 50, m2 is 100, and so v2 must always be negative 1/2 v1. So it's always going the opposite direction, to the left rather than the right, and with half of the magnitude. So given that, we can now say that our kinetic energy, which we know the value of 8.34 times 10 to the negative ninth, should be 1/2 m v1 squared plus 1/2, this is m1 v1 squared, m2 v2 squared. And then v2 we can just say is half the magnitude of v1. So this will be 1/2 m1 v1 squared plus 1/2 m2, and then just 1/2 v1, and then that whole thing squared. So now plugging in the values for m1 and m2 and using our value for kinetic energy, we can get then that v1 is equal to 1 point, oops, maybe we'll come over here. v1 is equal to 1.49 times 10 to the minus fifth meters per second. And so we could go back to an equation then solve for v2, but also we know that v2 has to have half the velocity. We already found that. So just dividing that by 2, we get then that v2 must be 0.746 times 10 to the minus fifth meters per second. And this is with the minus sign, it's going to the left, so opposite direction. And finally then, the relative velocity of these two. So how fast are they kind of closing the gap between each other? Well, we just can add up the magnitudes of the velocities. So this one is moving at one speed, this one's moving at the other speed. And so that total relative velocity, just 1.49 plus 0.746, gives us 2.24 times 10 to the minus 5 meters per second. And finally now, so part C, we want to know how long from the, or how far from the center of the 50 kilogram sphere do the two spheres collide. So I can say I know that the initial distance between the two spheres is 40. And so at some point they've collided, and sphere 1 will have traveled a distance x1, and sphere 2 will travel a distance x2. So together they must have traveled 40 meters in order for them to have closed that gap. And so then, because we found that the velocity of sphere 1 is always going to be twice that of sphere 2, that means that sphere 1 will have always traveled twice as far as sphere 2. So any time value we want to plug into a position equation, if we're using twice the velocity for sphere 1, it's always going to have gone twice as far. So we can write this then as x1, and then x2 is just half the value of x1. And so then we get 40 equals 3 over 2 x1, and we find that x1 should equal 26.6 meters. So that leaves x2 then as about 13.4 meters. So about, within rounding error, half the value of the distance x1 traveled. So that all seems to check out.